Start with the sound the planet makes when it rings like a bell. The clues were millisecond scars on decades of seismograms. The smoking gun, earthquake echoes, and time lag twins. To understand a heart, you listen for a beat. For Earth, that beat is the PKIKP phase. Seismic waves that dive through the liquid outer core, punch across the solid inner core, and climb back out. When the same kind of earthquake takes the same route years apart, those waves should arrive in lockstep. They don't, and that tiny drift is the tell. The heroes of this story are doublets, near-repeat quakes from places like the South Sandwich Islands. Picture two quakes along the same fault, similar size, similar path, separated by years. Seismologists stack their signals and go hunting for a few thousandths of a second in difference. It's absurdly small, coffee spill small. But when a planet's core changes speed relative to the mantle, that's where it leaks through. Here's the stakes. If the inner core speeds up or slows down relative to the crust, the anisotropic iron crystals inside, those that preferentially pass waves faster in certain directions, rotate with it. The path stays the same, but the texture the waves cross has turned a little. The phase arrivals drift. On paper, it's a wiggle. In reality, it's a global metronome, phasing with itself. Action. In the 1990s and 2000s, travel times of PKIK compared to later core phases showed a pattern. The inner core seemed to be super rotating, slightly outrunning the mantle. Then the drift eased. Since around 2009, multiple teams noticed the differences narrowing, even reversing sign in some pairings. In 2023, Song and Yang, Nature Geoscience, argued the inner core was slowing relative to the surface and heading into a downswing of a decades-long oscillation. In 2024, a broader waveform study in Nature added fresh doublets through 2023 and found backtracking, a reversal relative to the mantle, at a rate around 0.05 to 0.15 degrees per year. That isn't a literal stop, it's a change in the lead lag between two nested spheres. Impact. Those numbers mean the inner core's orientation, as felt by seismic waves, is shifting on human timescales. It suggests a natural multi-decade cycle, not a one-way crash. But when the cycle hits a slowdown, the forces coupling the core and mantle, the very ones that steer the geodynamo, are also rebalancing. That's where the surface consequences may emerge first, not as earthquakes or volcanoes, but as quirks in the magnetic shield. Meanwhile, something else was happening. Independent methods started lining up. Normal modes, the planet's free ring after giant quakes, hinted at similar rotation rates. Coda waves that scatter inside the core showed consistent changes. Inner core backscattered waves, a hard-to-catch reflection from deep inside, pointed the same direction. When different techniques with different biases converge, scientists take notice. The evidence isn't one instrument with one idea, it's a chorus. What nobody knew at the time was whether the slowdown was a kink or a rhythm. Some teams suggested a 70-year oscillation, consistent with Song and Yang 2023, with alternating decades where the inner core leads, then lags. Others argued for shorter cycles, 20 to 30 years, based on different stacks and statistical windows. The debates got sharp because the shifts we're measuring are so small that how you pick, filter, and align the waveforms can tilt the answer. But the broad shape held. The mid-2000s were a pivot. The 2010s showed a deceleration relative to the mantle. The early 2020s added evidence for backtracking. Here's the human moment. A researcher at a northern array pulls up a new South Sandwich doublet. Two traces look like carbon copies. Then the cursor nudges 0.02 seconds. That's it, a breath. But it's consistent with 5 other paths from the same region and nearly a dozen new events. She leans back, realizing those 2 lines are the sound of the planet's core slipping phases with the surface we live on. But there was one problem. A change in arrival time could, in theory, come from something else, like evolving anisotropy, a rearrangement of crystals without bulk rotation change, or subtle variations in the outer core flow that bend paths. That's why the teams didn't rely on a single kind of wave. They cross-checked PKIKP against other core-sensitive arrivals and looked for coherent waveform distortions, not just first clicks. They tracked antipodal stations, used arrays in Alaska and Canada, and kept adding fresh doublets as new quakes happened. The pattern persisted across methods and instruments. This was the moment everything changed. When the waveform studies through 2023 extended the timeline and still saw the same directional pivot, it turned a possibility into a trend. If the inner core is indeed in the downswing of an oscillation, then electromagnetic coupling between the liquid metal flows and the solid core must be redistributing torque. That can tweak the geodynamo, the chaotic dance that builds our magnetic field. In the aftermath, attention turned upward. If the inner engine is changing rhythm, the magnetic field should respond with subtle but trackable signatures. Shifting flux patches under Africa and South America, more turbulence in the South Atlantic anomaly, and a continued long-term dipole weakening. None of that proves cause and effect by itself, but when the heartbeat slips and the shield stutters, you don't ignore the coincidence, you test it. To understand why the inner world might be tapping the brakes now, we need to leave the seismograms and dive into the coupling zone, where metal flows grab iron, field lines twist, and continents above quietly push back. Because if the echoes were the message, the torque is the hand that wrote it. The tug-of-war core mantle coupling and magnetic friction. Start where the echoes point, at the boundary between the inner and outer worlds. Microstory. A modeler in Boulder runs two core flow simulations side by side. She tweaks one parameter, a slight change in electromagnetic coupling strength at the inner core boundary. In one run, flux patches under Africa hold. In the other, they shear and drift west faster. Same heat, same chemistry, just a different clutch setting. Her takeaway is simple. A tiny torque change deep down can redraw the magnetic map we live under. The inner core is a hot, solid iron nickel sphere. Around it, the outer core is a roiling ocean of liquid metal, moving in loops and jets that generate the magnetic field. Above that, the mantle is sluggish rock, but it's heavy enough to matter. None of these layers spin in perfect lockstep. They negotiate, they tug, they compromise. Here are the stakes. If the torque balance shifts, if magnetic grip strengthens or weakens, if mantle gravity leans harder, then the inner core's lead or lag changes, and the geodynamo's geometry tilts with it. That means where magnetic field lines emerge and dive can drift, wobble, or fray. The consequences are quiet for a while. Then satellites start logging errors. Auroras spread to strange latitudes, and power operators get nervous. Action. Inside the outer core, convective flow twists magnetic field lines into spirals. Those lines thread the solid inner core. Because iron conducts, the changing field induces currents in the inner core, and those currents feel a torque, electromagnetic coupling. Think of it as a magnetic clutch. When the outer core flow tries to drag the inner core along, the clutch engages. Meanwhile, the mantle's uneven.
Gravity, shaped by deep structure in the continent's mass above, tries to align the inner core a certain way. That's gravitational coupling. Add in the fact that the inner core's surface isn't smooth, it's lumpy topography. Fluid shears across those bumps create viscous and pressure torques, three hands on one wheel. What nobody knew for sure until the slow pivot showed up in waveforms was which hand was tightening. Multi-decade oscillations have been proposed. Flows reorganize. The magnetic clutch tugs the inner core forward for a spell. Then the mantle's gravitational alignment and core mantle boundary heat flow asymmetries push back. The result is a swing, lead, then lag, on timescales of decades. A slowdown in the 201s fits a downswing of that pendulum. Impact. When electromagnetic coupling dominates, more rotational energy moves into the fluid, stirring the dynamo differently. That changes the distribution of flux patches, regions where field lines are concentrated at the top of the core. The African and South American patches that underlie the South Atlantic anomaly become especially important. If those patches weaken, drift, or split, the field above thins. A subtle torque change deep below becomes a radiation map in orbit. Meanwhile, something else was happening near the boundary. Heat leaving the core into the mantle isn't uniform. Where the lowermost mantle is hot and sluggish, less heat escapes. Where it's cooler and dense, more heat siphons out. That pattern sets the lanes for outer core convection. Large-scale mantle features, like the African and Pacific superplumes, may gate where fluid rises and falls, and therefore where magnetic field is generated strongly or weakly. In other words, continents and deep mantle structures don't just sit there, they steer the dynamo by shaping the heat budget. But there was one problem. Friction. Not the sandpaper kind, magnetic friction. When field lines connect a moving fluid to a solid conductor, they can convert differential motion into heat.
It's tiny, but over years it matters. Think of bumper cars at 5,000 kilometers down, except the cars are molten iron and the bumpers are magnetic springs. Every jostle damps a bit of relative motion. In a downswing, that damping can help the inner core lose its lead and drift into lag. Action on the mantle side, tides, topography, and slow continental drift. Earth tides flex the whole planet by centimeters daily. At the core mantle boundary, those periodic stresses can modulate flow and pressure, altering the torque environment. Mantle mountains at the boundary, kilometers of relief frozen into deep rock, shape how fluid scrapes past, changing shear and drag. Even the redistribution of mass by supercontinents over millions of years leaves long-lived fingerprints on the torque balance. On human timescales, that's not shifting fast, but it sets the baseline the magnetic clutch works against. Stakes again, concrete this time. If torque redistribution is nudging the dynamo into a less stable geometry, you expect signals. Faster westward drift of flux lobes, growth and splitting of weak field regions, more jerky secular variation. That's what observatories and satellites have been reporting. It's not proof that the inner core slowdown caused it. Both could be responding to the same deep reorganization. But from a risk perspective, causation is less urgent than correlation that persists. Here's where it gets tricky. The inner core itself isn't a uniform ball. Its iron crystals have preferred orientations that can evolve as new solid iron freezes onto its surface from the outer core, inner core growth. There's evidence for a snow zone at the top of the inner core, slushy crystallites that settle like metallic snow. That slurry can change how torque is transmitted, acting like a seasonal slick on the clutch. If the snow layer thickens or thins with changing heat flow, coupling strength shifts. Now your pendulum has a moving pivot. Micro story. In Paris, a lab team stirs a tank of salty water over a rough sphere to mimic shear across a bumpy boundary. Add a thin gelatin layer to imitate snow, and the drag drops. Remove it, and the flow bites harder. The plots on the wall aren't the core, but the pattern is universal. A thin layer can flip how a system transmits force. Impact, immediate and practical. A slightly weakened coupling that lets the inner core lag a bit more can redirect where field lines bundle at the core mantle boundary. The surface field then trends weaker in those regions, and satellites crossing overhead take more hits. Airline operators see higher radio noise on polar routes during solar storms. Grid planners model larger geomagnetically induced currents for the same solar wind input. The machine still runs, but the tolerances slip. So, the tug-of-war isn't a single rope with two teams. It's a braided mess. Electromagnetic clutch, gravitational alignment, viscous drag over a lumpy boundary, heat flow,
Patterning, and a snow-dusted inner core surface, all adjusting at once. The seismic pivot told us the balance changed. The field's behavior hints at where it's going. If the dynamo is stuttering, the magnetic shield will show it first, and it already is. Symptom number 1, the South Atlantic anomaly isn't waiting. While torque shifted in the deep, a bruise spread across the sky. The South Atlantic anomaly, SAA for short, sits over Brazil, the South Atlantic, and nudges into southern Africa. To a satellite operator, it's a no-fly zone you can't avoid. Pass through, and your instruments face a rain of energetic particles that the magnetic field would normally deflect. Memory bits flip, star trackers lose the sky. Sometimes the whole spacecraft slips into safe mode to ride it out. Here are the stakes. The weaker the field over this patch, the deeper the inner edge of the radiation belts dips. That puts the flow of charged particles right in the altitude lanes, where Earth observation and science satellites live. The difference is measured in glitches and resets. On the surface, it's easy to shrug at a quiet region of magnetism. In orbit, it's the one corridor you plan around every single day. Action. Over the last decades, maps from missions like Orsted, CHAMP, SWARM, and ground observatories have watched the SAA expand and drift west. Within the broader oval, smaller hotspots form and merge cores of even lower intensity. Think of it like an eddy splitting off a current and then rejoining downstream. Operators learn the rhythm. Schedule software uploads outside the SAA window, harden the most sensitive electronics, add error-correcting memory that can tolerate cosmic confetti. Hubble's ops team built their calendar around it. They suspend observations while crossing the anomaly because the risk of detector hits is simply higher. Meanwhile, something else was happening beneath the map.
It cell lines up with weak field flux patches at the top of the core under Africa and South America. Core flow models show these patches drifting and reshaping, which helps explain why the anomaly migrates and splits. That fits our torque story. If the deep engine's geometry is shifting, the top of core pattern should move, and the surface field responds. You don't need a full reversal to complicate spaceflight. You just need a persistent thin spot that keeps thinning. Impact, immediate, and mundane. Satellites crossing the SAA report spikes in single event upsets, SEUs, where a single particle flips a bit in memory. Most are corrected, some aren't. That's when you see safe modes, system reboots, and occasional instrument restarts. The European Space Agency and NOAA bake SAA statistics into risk estimates for their fleets. Commercial operators do the same. For crewed missions, dose adds up. It's not just one pass, it's thousands over a career. Flight surgeons track it like they track hours in high latitudes. Airlines feel it at the edges. At cruising altitude, you're still under the bulk of the atmosphere. But during strong solar events, the extra ionization over weak field regions can add noise to high-frequency radio and marginally bump radiation doses on long-haul routes. Most days it's trivial. On the wrong day, with the sun flaring, dispatchers reroute and pilots use alternate comm bands. Every detour costs fuel and time. Multiply by a fleet and a year, and it's a line item. What nobody knew in the early anomaly maps was whether this was a phase or a path. The trend says path. The dipole, the global bar magnet part of the field, has been weakening since the 19th century, and the SAA rides that decline. The anomaly's westward drift matches the westward drift of flux lobes we track globally. And inside the SAA, those hotspots that come and go, they're telling us the core's flow isn't smooth. It's reconfiguring in steps. Here's a micro story. A satellite engineer in Darmstadt watches telemetry tick to red as their spacecraft enters the SAA. The onboard computer logs a burst of corrected errors, then one that isn't. Safe mode. Cameras close, reaction wheels idle, pointing goes soft. 20 minutes later, after exiting the anomaly, they coax it back to life. It's routine. It's also an invoice. Lost science time, ground station minutes, fatigue for a team that now expects the Brews to push a little farther west next year. But there was one problem. The anomaly is a symptom, not a diagnosis. Weak field could come from any combo of deep changes. Flux patch drift, core flow accelerations, or a subtle change in coupling at the inner core. We can't point from the SAA to a single cause. What we can do is measure its growth, tie it to the broader secular variation, and plan for more of it. The SAA isn't waiting for a headline about reversals. It follows the physics. If the dynamo's geometry keeps sliding toward less stable patterns, the bruise will deepen, and every orbit that crosses it will pay a toll. Symptom number 2, a field that's bleeding.
Strength. While the SAA makes headlines, the background story is the slow fade of the whole shield. Since the 1800s, observatories have watched Earth's magnetic dipole, think the bar magnet part of the field, lose strength. It's not a collapse, it's a steady leak. The numbers aren't abstract to the people who map them. Every decade, the contour lines shuffle. Instruments that once agreed need recalibration. The compass still points north, but that north is less bossy than it used to be. Here are the stakes. A weaker dipole means more solar and cosmic particles can thread the upper atmosphere, especially during storms. It also means the field gets patchier, with regional highs and lows that shift faster than maps can age. Navigation systems lean more on models. Satellites face a noisier sky more often, and when the sun shoves, the ground pushes back. In power lines, in pipelines, in rails, through currents that weren't there before. Action. The field isn't a static dome. It's a living pattern of flux lobes, bundles of field lines that drift westward like weather systems. For 2 centuries, that westward drift has been a quiet metronome, measured first by ships and compasses, then by satellites like Ørsted, Champ, and Swarm. As the lobes slide, they reshape where the field is strongest and weakest at the surface. Pair that motion with the dipole decline, and you get a map that looks more restless every year. Meanwhile, something else was happening deep below. Core flow models that assimilate satellite data show jets and gyres at the top of the outer core speeding, slowing, and sometimes reversing lanes. Those changes line up with shifts in flux patches beneath Africa and South America, the same underpinnings that feed the SAA. It suggests the dynamo is in a reconfiguration phase. Not broken, not calm, just moving furniture in a cramped room. When furniture moves, toes get stubbed. Impact. The scary part isn't that compasses will go haywire tomorrow.
It's that instability rides with weakening. A thinner shield feels storms more. During a strong coronal mass ejection, more energy can couple into the magnetosphere and ionosphere, amplifying geomagnetically induced currents at the surface. Power grids see reactive power swings, transformers heat up from stray harmonics, and protections designed for yesterday's storms run out of margin. Quebec, 1989, wasn't the biggest storm imaginable. It was big enough with a stronger field than today's. GPS doesn't want to cosplay as a treasure map from 1702, but under a wavier ionosphere, stirred by solar ultraviolet, particle precipitation, and the field's own changes, signals refract and delay unevenly. That injects errors that need real-time corrections. Aviation, precision farming, drilling, they all bought accuracy on the assumption that corrections would keep up. They do, mostly. During storm peaks, mostly turns into call your backup. Pipelines learn the hard way. Indigenous to their business is cathodic protection, small currents that keep steel from corroding. Geomagnetic storms induce currents that ride those same lines, flipping protection on its head and accelerating corrosion in the wrong spots. Operators have monitors, but a field that's bleeding strength means more days per cycle, where the induced current budget gets tight. Maintenance moves up the calendar. What nobody knew for sure was how much the inner core's rhythm mattered to this bleed. The geodynamo is mostly an outer core show, driven by heat and composition. But flux load behavior hints at deeper influence. If the inner core's lag alters how field lines anchor and slip, the outer core's flow responds, and the secular variation, the slow drift of the field, picks up new quirks. You don't need a grand reversal to get messy maps. You need a slightly different clutch setting for a decade. Here's a micro story. A grid operator in Northern Europe runs a storm drill. The inputs look routine, another solar wind stream from a coronal hole, but the model flags higher induced currents than the last time a similar stream hit. He checks the KP forecast again. Same. The difference isn't the sun, it's the ground's magnetic stiffness trending looser. He calls for extra reactive reserves anyway. Later, during the real event, the alarms stay quiet. It's not drama, it's prudence, informed by a field that gives up a little more each year. But there was one problem. Decline isn't destiny. The field waxes and wanes over centuries. Paleomagnetic records show long recoveries after slumps. The concern now isn't a mythical instant flip. It's the convergence of weaker baseline, rising tech dependence, and a solar cycle heading toward peaks that repeat whether we're ready or not. A field that's bleeding strength doesn't guarantee disaster. It guarantees that the next punch lands harder.